Okay. So, today the uh, firstly we'll determine the fundamental group of the punctured plane. So to determine the fundamental group of the punctured plane, as we have already shown that these two groups are isomorphic. We are going to show that these two groups are isomorphic. Okay, but how? Now let me have a uh, look on that. That suppose you have two maps. Suppose you have two continuous maps. Let it be, one is capital H, small h, and small k from the space X to the space Y, keeping in mind that this X, H of X naught will be mapped to Y naught and K of X naught will be mapped to Y naught. Okay. And if the image of the base point, so that means, so you have this space X and this is your Y. So you are doing something, so this is your X naught. So assuming that the image of this base point X naught in X remains fixed at Y naught. Okay, during the homotopy. That means we are assuming that this H and K are two paths, are two maps which are homotopic to each other. Okay. So suppose this is your H, this is your K. Yeah. And this is your K. Great. Now one can deduce that. So certainly for corresponding to this H, you are having the induced homomorphism H star, which is from pi1 X naught to pi1 Y naught, right? Suppose this is your H star. At the same time, you are having another induced homomorphism from pi1x to pi1y, which is K star, right? Now, since these two maps are homotopic to each other, keeping in mind that the base point X naught remains fixed at Y naught during that homotopy. Okay. So then one can prove that this is an easy exercise, that these two homomorphisms will coincide. Okay. Just using the definition, and certainly you will get the result. Okay. And following which, now, so our goal is that to determine the fundamental group of punctured plane, and we are going to show that this is isomorphic to the fundamental group of S1. But how? We have already seen the map, the restriction R from the punctured plane to S1, right? Just by collapsing each point of R2 minus 0. Okay. So each point to this one. Okay. So that means the formula of this R will be, so I'm taking each x is vector x to x by dividing by the norm. Okay. And this is going to be a retraction, as we have seen. And also there is there is an inclusion from S1 to this. And this inclusion will induce a 1-1 homomorphism, which is the induced homomorphism. Right? This is a 1-1. Sorry. And therefore, now one needs to check that. So it remains to check that considering any loop based at a loop in the punctured plane based at B naught, you need to produce a loop in S1 based at B naught, which will be associated by this map, right? So that means this should be surjective. But why? Because suppose you take any loop in the punctured plane based at B naught, suppose it is Z. So a loop in this based at B naught. Okay. And corresponding to this loop, what do you have? So that means suppose this is your S1 and you are considering a loop okay. Suppose it is your G. Now you are trying to map this G just by making a uniform structure and make it a round one to put it on S1, right? By this retraction R. So that means so this R composed G that will give you a loop in S1 based at B naught, right? Great. And this loop will do the job in that case. Why? Because of this reason that if you consider the inclusion map here, and we have already the retraction, so you can be able to think of this map J compose R, and this is a map from, so this is a map from the punctured plane to the punctured plane, right? So taking each x from the punctured plane to the unit vector along the line joining 0, 0 and x, right? That means x by, so this takes x to norm x, well, x by norm x, okay. And this is a continuous map. And another map that you can think, which is the identity map, right? The identity map. Okay. So therefore, you can always define a homotopy between these two maps just by what means? Just by taking each point of this here to here, right? Taking each point here to this. So I'm doing this all over. Okay. That means you are considering a line segment from the point X. This is your X, and you are projecting it to X by norm X. Okay. So therefore, so this is your homotopy, which sends to X comma T to the line segment joining the point X and the point in the unit circle, right? And using this homotopy, you can say that. So this implies the map J compose R is homotopic to the identity map. And once it is done, this will imply that you can compose these two maps with the loop, which is G, and this J compose R, compose G will be homotopic to the identity map, compose G. That is, this J compose R, compose G will be homotopic to G. And therefore, so this proves our claim, right? Because corresponding to this G, you are having R compose G, as we have said. And their path, they are homotopic. The map J compose R compose G is homotopic to G. Okay. And this proves that. So therefore, the J star is from S1 B naught to the fundamental group of the punctured plane and isomorphism. Okay. So therefore, this fundamental group is nothing but it is also an abelian group, which is Z plus. In fact, it is an infinite cyclic group, right? And according to the discussion that we have already mentioned above, this does not affect, if you want to generalize this discussion to Sn. Okay. That means one can prove that in general that the fundamental group of the punctured space n plus one dimensional space, Euclidean space, based at B naught. Here B naught is the unit vector along the first coordinate axis, right? So this will be isomorphic to the fundamental group of Sn. Correct. Okay. And this can be proved to be the space is simply connected, right? So since this space is simply connected, so if you take any closed path in it, then it will be shrunk to some point continuously. Okay. And deleting any finite, any countably many points from an n-dimensional Euclidean space doesn't affect the path connectedness. So therefore, it is simply connected, and this group will be a trivial group, right? We can also prove this in another way, and that proof will give you another another important theorem in topology, which is called Seipert-Van Kampen theorem, but we'll be looking later. Okay. So now I am trying to show that. So here, if you look at the picture, so that means, so if you are considering a G, then you are trying to project it to the S1 by means of the retraction, right? Through a straight line homotopy. Okay. And this observation gives you a direction to define what do you mean by a deformation retract, right? So that means, suppose you are considering a subspace A, a subspace of X, okay? Then it is defined to be a deformation retract of X. So if you look at this case, so you have two maps, right? One is the identity map. So this map plays an important role in this situation. So this identity map you can consider on X. So if the identity map, let us call it IX, will be homotopic to a continuous map. So that will be homotopic to a continuous map like that J composer, okay? Like this one. Okay. So we can say that we can define, we can think of this map like this, that a continuous map that carries all of X into A, such that A remains fixed during the deformation pointwise. Okay. So a continuous map which will project every point of X into A, satisfying that if you restrict this map to A, it will be the identity on A again. Okay, so that A remains fixed during the deformation. Pointwise. Okay. Great. So analytically speaking, so you must have, so that is, you must have a continuous map from the cylinder okay. So this is your X cross I to X. Okay. So if you can produce a continuous map H from this X cross I to X, satisfying that at the 0th level, it will give you the identity map, that is H0 will be the identity map on X. Okay. And if you look at the 1th level, okay, then this will be the identity map on A. Okay. And not only that, you can see this, that during the deformation, A remains fixed. Okay. So that means H A comma T must be A, or all A belongs to this. That means if you want to restrict those maps HT to A, that will be the identity map. Okay. So not only H1, if you take any T, and if you want to restrict that to A, that will be the identity map. And H1 must be the identity map. Okay. So in this way, you can define deformation retract, and this H will be called a deformation retraction. Of X onto A. Okay. And I have already given a very particular kind of example of, that is a thin A and a fat A. So you can also take that as an example, okay, which was given in the previous session, and you can make it a, so yeah. So this skeleton A, so this is going to be a deformation retract of this fat A. Okay. 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 So that means, so if you look at this H, so this defines a retraction. What is that? So remark that if A be a deformation retract of X, then corresponding to that H, then we define a retraction. What is that? Defined by R, which is defined by this rule, that is each X will be mapped to where? HX1. That means so that H1 will give you the retraction, right? So every X will be that one. Yeah. Oh, I'm sorry. Sorry. Yeah. This shouldn't be IA. Yeah. H1 of capital X. Yes, subset of A. I'm sorry. Yeah. Great. So so that means, so from this retraction, now you can make a comparing here for that example given in the punctured plane. This J compose R and this identity map. Now you have this retraction R smaller. So that means you are going to set up a homotopy in between J compose R. What is J? J is the inclusion map from A to X, right? So this J will be a map from X to X. And also you have this identity map, right? And this H, so these two maps are homotopic via H. Okay. And so how this notion of deformation retract will help us in determining fundamental groups just by using this result that if A be a deformation retract of X, and if you choose any point from A, okay, then so if A be a deformation retract of X, and suppose you take a point, let us call it A naught. So then you have a choice of map, which is the inclusion. So this inclusion will induce an isomorphism. Okay. So this will induce an isomorphism, which is the induced homomorphism, right? That has been visualized here in this case. That just where it is, yeah, this one, right? So great. So this J star will be an isomorphism from this fundamental group to the fundamental group of X. Okay. So that is, so if you take that deformation retract, so the fundamental groups are isomorphic. Okay. Great. So after doing this identification with these two groups isomorphically, one will see that not only the punctured plane, if you look at this space R3, okay, and this is your XY plane. So this XY plane, let us call it R2 minus 0. Right? Now, if you want to delete the Z axis from R3, okay, so we take R3 minus Z axis. Okay. Then what will happen? Then what you are doing, you are just crash down the points in the upper half space to that XY plane just by making these identifications. Right? And taken up all the points from the lower space to this XY plane. Then what will happen? And forget about that, you are deleting Z axis. just z-axis be remained here, and you are cross down this collapsing the points of z-axis, this one, and from the lower z-axis to this one. Okay. So that means you are getting, so now if you want to delete that z-axis, so that means, so from this one, you are having the, right? So in this way, we see that this R2 minus 0, which is the xy plane, is a deformation retract of R3 minus z-axis, right? And therefore, in view of the previous result, which has been settled that the fundamental groups are isomorphic, so therefore, so this one minus z-axis, this is isomorphic to the fundamental group of punctured plane. Deleting a point, based at the point B naught. Okay. So that means it is isomorphic to Z plus. Okay. This is a very nice example. And another example, which will give you a very nice kind of space. And this space will be an example of a space having non-abelian fundamental group. Okay, which is the figure 8 space. So what would be the scheme of doing this deformation? So suppose you take, now you want to take the plane punctured at 2 points. Okay. So suppose, so now let us choose X as this punctured at 2 points. Okay. So what you are doing? So I'm referring to this picture. Okay. So suppose you take, for the sake of convenience, let us take 2 points here and here. Okay. Suppose this is your P and this is your Q. And supposing that this is your unit circle or any circle which is homeomorphic. So any circle is homeomorphic to S1. So you can take any one. And you are taking the retraction of each point of that plane to this circle, the outside of that circle. Okay. Yeah. So that means it gives you a resulting one, which is going to be something like this, that is this circle and 2 points, right? Okay. Now we are taking 2 circles around centered at, one is P, another one is Q. Let us call it P, let us call it Q. And you are taking 2 circles touching at a point. Yeah. And now projecting each of the points here, either to this one or to this one. Okay. Yeah. So that leaves another space. So now you are having two disk, closed disk, having centered at P and Q respectively, and touching exactly at that common point. Okay. And now what you are doing now, you are projecting each of these points, since here is a puncture. So here is a puncture at P, here is a puncture at Q. So you are projecting the other points to these boundary circles. Okay. Correct. And that gives you another resulting one, which is something like the number 8, right? That is yeah. So this is going to be, so this space is called the figure 8 space. Okay. And let us denote it by this one. Okay. And this space is equipped with the topology induced from the usual topology in C2 cross C2, right? So you can see that what would be the covering space. We can check that this space is homeomorphic with this one. Suppose let us call it X, let us call it Y, and make it homeomorphic with this space, right? Union B naught cross S1. Okay. Yeah. So this is the union of two circles having one point in common, and it is equipped with the usual topology in C2 cross in in C2 cross C2, right? No. What would be the topology here? Yeah. C cross C, right? Yeah. Great. So now, with respect to this Y, what you can do, so now you can consider, since here you have make a choice here, you are taking S1. So this S1 will be giving the usual covering map, which is P, right? So this is the usual covering map, and we are taking the base point as so this B naught as it is 1, 0, right? And now you want to consider the product of this covering map P cross P, which is from R2 to the torus, which is S1 cross S1, right? Great. So therefore, so this Y is a subspace of this torus, right? And we take the inverse image of Y with respect to this covering. Okay, let us call it Y tilde. And what is that? You can check, this is nothing but So this will be R cross Z union Z cross R. Okay. Because you need to consider the equations, which is for one is for this P and another one is for this P. So S and T satisfying that e to the power 2 pi I t, which will be 1, and e to the power 2 pi I s is 1, right? So this two will give you that that for that case, that is for this one you will get, so for this S1 you will get R, and for this B naught you will get Z. For this B naught you will get Z, and for this S1 you will get R, right? So that is why I am writing. So that means it is a infinite grid of lines in R2 comprising of horizontal and vertical lines that are passing through the integers. Okay. So that means infinite grid of lines. Okay. Okay. So suppose this is your 0, 0. This is 1, 2, 3, 4, and so on. And let us take here also -1. This is 1. Okay. And in this way we can, this is 2, this is 3, and so on. Yeah. So each of these point having coordinates integer valued. Okay. Great. And you can check that since we have already seen this P cross P is nothing but it is again a covering map. And we are taking the restriction of this map at y tilde. So this restriction, let us call it P cross P y tilde. So it is a restriction to this. So this is nothing but, let me, yeah, P cross P restricted to y tilde, and it is a map from this to y. And this is a covering map by using a known resolute, right? And therefore, this says that that infinite grid of lines in the plane will be a covering space of the figure 8 space. Again, if you look at the plane punctured at 2 points, you can also have a space which is called theta space. Also, if you look at the deformation, you can, if you want to make the deformation in this way, that is suppose, so again we are taking 2 points P and Q here, and we are taking a circle. Okay. Now we are going to consider this part, this segment also. And what we are doing, firstly, this is a natural retraction, that is projecting each points outside that circle to this circle. Okay. And you are getting the resulting space. Okay. This one. So this space having punctured, having 2 punctures, one is at P, another one is at Q. And therefore you are going to project each points in this space. So here, here, okay, in this way. That means that can be taken up as here. So this gives you the resulting space, which is nothing but, which looks like this. Okay. So this is called the theta space. And you can see that likewise the above, the fundamental group, the fundamental group of the plane punctured at 2 points. This is isomorphic with the fundamental group of the figure 8 space, right? Not only that, in this case also, we see that the fundamental group of this plane punctured at 2 points will be isomorphic to, let us denote it by theta. Okay, so pi 1 theta. Okay, great. So what we have done, that the figure 8 space and the theta space both have isomorphic fundamental groups, right? So this figure 8 space and this theta space both will have the isomorphic fundamental groups, which is the fundamental group of the plane punctured at 2 points, right? But it should be noted that neither is a deformation retract of the other. So between these two spaces, figure 8 space and theta, neither is a deformation retract of the other, but their fundamental groups are isomorphic. So this example motivates us to think that the possibility that maybe you will have isomorphic fundamental groups of two spaces, but the spaces will not be the deformation retract from each side. Okay. Good. Okay. So this says that, but there is you can make an association in between these two spaces. And for this one, you need to go up, right? You need to generalize the notion of deformation retract. So what would be that notion? That is what we are calling it homotopy equivalence. Okay. So analytically, it says that, so if you want to write down the definition formally, so it looks like this. Suppose you have a space and you have another space here. Suppose it is your X, it is your Y, and you are considering two continuous maps. One is from, suppose, let us call it F, and another one is from Y to X, which is G. Okay. So two continuous maps. Great. And suppose that, so you can easily make the composition G compose F and F compose G both. So G compose F. So if we let that this G compose F is homotopic to the identity map on X, and F compose G is homotopic to the identity map on Y, then we call these maps as homotopy equivalences. Okay. Then we call F or G as a homotopy equivalence. Okay. And each map is defined as a homotopy inverse of the other. Okay, so G or F, whatever you choose, is called the homotopy inverse of F, and vice versa. Okay. So in this way, you can define a relation in a class of spaces. Okay. So if you consider a class of space, topological spaces, you can say that if you take any two space X and Y, so these two space X and Y, so this X is said to be homotopy equivalent to Y if it can be possible to construct a continuous map from X to Y such that F is a homotopy equivalence. That means if you can find out a map from Y to X such that that map will be the homotopy inverse of F. Okay. So X and Y are defined to be homotopy equivalent if for some continuous map F from X to Y, there exists a homotopy inverse of G of from Y to X. Okay. And this relation of being homotopy equivalent certainly will be an equivalence relation. Okay. So fact that being homotopy equivalent will be an equivalence relation. That means you can partition the class of spaces by means of this relation to have some similar kind of space, right? So that kind of situation can be demonstrated in this way that two spaces are said to have the same homotopy type if they are homotopy equivalent. Okay, that means if you take any space and if you consider the equivalence class of that space, so each of the member of that class are of same homotopy type, right? Great. So homotopy type means so X is said to have the same homotopy type as that of Y if X and Y are homotopy equivalent. Okay. Great. Now, using this notion, now let's move back to the notion of deformation retract. Suppose you have a deformation retract of a space X, then you can say that. So if A is a deformation retract of X, then what can be said about A and X? That space A will belong to the equivalence class of X. That means A will have the same homotopy type as that of X. So then A will have the same homotopy type as that of X. Because, what is the reason? Because you have the retraction, which is from X to A, and you have the inclusion, right? From A to X. Now, what you are supposed to do? So, you need to check that. So, this R compose J, so this J compose R is what? It is homotopic to the identity map on X, right? Likewise, if you take the another composition, that means R compose J, this is nothing but the identity map on A. So that means this R compose J is automatically, it is homotopic to the identity map on A. So this gives you that identification between A and X, that is, they will have the same homotopy type. So they are homotopy equivalent. Okay. Therefore, following which, you can make a note here that if two spaces will have same homotopy type, they will have isomorphic fundamental groups. So if two spaces will be having same homotopy type, then they must have isomorphic fundamental groups. I'm sorry. Right? Okay. So, great. So therefore, if you let that, so if X and Y are two, so if let us consider two spaces X and Y, and suppose that you can find out. So if it is possible for you to construct a homotopy equivalence in between X and Y, suppose it is F, homotopy equivalence, satisfying that, you need to choose a base point in X and a base point in Y, and you need to connect these two base points by this map. That means if X naught must be Y naught. Then this homotopy equivalence will induce an isomorphism in between the fundamental groups of the respective spaces. So then this will induce an isomorphism, which is F star from the fundamental groups, from the fundamental groups of fundamental group of X to the fundamental group of Y. So, which is implying that they are isomorphic, right? So this is the case. So the concept of homotopy equivalence is a more general kind of notion compared to deformation refraction. And it should be noted that the figure 8 space that we have seen earlier, figure 8 space and the theta space, both are deformation retracts of the doubly punctured plane, right? But neither is a deformation retract of the other. But in terms of homotopy equivalence, you can say that they are homotopy equivalent to the doubly punctured plane, and so to each other, because the relation of being homotopy equivalence is transitive, right? So this is the case, but you cannot say that the figure eight space is homeomorphic to a deformation retract of the other. Okay. So this cannot be proved. Okay.
Can I ask a question?
Yes.
Yes. So the definition so
Sorry, I can't hear you properly.
yes. Sorry.
Can you drop your question in the chat box? Can you? Your voice is cracking actually. So yeah. Okay. Okay. Great. But generally, as we have seen for the figure eight space and the theta space, that they will have the same homotopy type. And it can be proved in general that if you take any two spaces, X and Y, they will have same homotopy type if and only if they are homeomorphic to deformation retracts of some single space. Okay, some space. Yeah. And in view of this notion, you can make another definition of contractible space. That means a space is contractible if and only if it has the homotopy type of a one-point space. Okay, let me see what is here. So if you are, we say that if there is homotopy, then we need what is okay? We say X and homotopy equivalent. No, whenever you are talking about the homotopy equivalence, you do not need to specify the base points. But whenever you are trying to determine the fundamental groups, then you need to welcome these base points into the picture, right? So this should be done in this way. But whenever you are relating that homotopy equivalence of spaces, so that is not needed. Okay. Yeah. Okay. Great. Now let's try to find out. Yeah, I should make a note here. I forgot. So a contractible space means a space X is contractible if and only if it has the homotopy type of a one-point space, of a singleton space. Okay. Yeah, that means X is a homotopy equivalent to a singleton. Okay. So you can see that in any n-dimensional Euclidean space. Okay. Now let's move forward to a very nice kind of space, which is okay. So let me just prove. So now let us set our goal to prove that what would be the fundamental group of Sn. For n equals to 1, it is not trivial group. It is a non-trivial group, but it is an abelian group. But if you are looking at higher dimensions, then what will be the case? Okay. And in that case, we will see that to tackle this situation. So if you can remember the notion of stereographic projection, so what you can do, so suppose let us take S2, and if you want to take a puncture at the North Pole, then that will be, so this is homeomorphic with Rn, right? Great. And let us make a flip with respect to the equator. Then you are taking a puncture at the South Pole again, right? So that will be again homeomorphic to Rn. I'm sorry, this is R2. Yeah. So in general, so this Sn minus n will be homeomorphic to Rn, and Sn minus S is homeomorphic to Rn also. Okay. And since they are homeomorphic, so you can make so if you want to take P as, suppose you take a P, so let us take a P here. Okay. So then pi 1 of this will be a trivial group, right? Because Rn is contractible. At the same time, you will get the same result for the sphere punctured at the South Pole also. So what does it say? So this implies these two spaces are simply connected, right? So these two spaces are simply connected open sets, and not only that, they are making an atlas of this sphere, right? That means if you want to check that, so this is so two open sets, and their union will cover this one. Okay. So this is an open set. Suppose it is, let us call it U, let us call it phi. And if you want to puncture, if you want to make punctures at N and S together, then you will have the intersection, right? So this implies, so now this U intersection V, that means you have executed two punctures at N and S together. Okay. But that remains. So this will be homeomorphic to what? Rn minus some point corresponding to that South Pole, right? So let us call it XS. Okay, great. So yeah, so this is since it is homeomorphic to this one, and this is a path connected space. So this is a path connected space, right? So this Sn has a cover, open cover, which is U and V, constituting U and V, which are simply connected domains having path connected intersection. Okay. Great. Now, generally, if we suppose that if we take the same situation for a general kind of space, so suppose that let us take any space X, which can be represented as a union of two open sets U and V, which are not only an open sets, but they are. So they are the open sets having path connected intersection. Okay. And if you let a base point, which can be specified in the intersection of that two open sets. So let us take a base point in this domain, path connected domain. Then what you are having here, then from so pi1 from the fundamental group of U to fundamental group of X, you can define the induced homomorphism, which is I star, right? Similarly, you can define the induced homomorphism from pi1 V to pi1 X using the inclusion of V2X. So this J star. So this I star pi1 U will be sitting inside this fundamental group. J star pi1 B will be sitting inside the fundamental group of X. And you can say that, you can conclude that the fundamental group of X can be generated by these images of the fundamental groups of U and V. Okay? With respect to I star and J star. That means it is the group generated by okay. And later we will see that in Seifert-Van Kampen theorem that you can set up a map from the free product of these two groups, pi1 U and pi1 V, to the fundamental group of X, which will be isomorphic. So the fundamental group of X will be isomorphic to the free product of these two groups modulo some normal subgroup, least normal subgroup, which will be the kernel of the map, right? So it can be proved later. But we will see this in this way, that what you need to prove. So that means you need to represent any member of this fundamental group by means of, that is, suppose you take a loop gamma here, and you are going to prove that the path homotopy class of this gamma, it is nothing but, it can be expressed as a free product of paths. I mean, here it is the concatenation of paths, right? So that means it is G1, let us call it sigma 1 star, sigma 2 star, sigma, let us call it sigma n, where the sigma 1, sigma 2, sigma n, it can be constructed in such a way that each of these sigma k, so it is a loop in X based at X naught, but that will be lying either in U or in V. Okay, so this is a loop in X based at X naught, lying either in U or in V. Okay, great. Now, since we are dealing with the paths, that means the maps from the closed interval 0, 1 to X, right? So that means you are concentrating on the compact space, compactness of this closed unit interval. Okay, and through this compactness of the closed interval, you can easily find out by means of Lebesgue number theorem. You can easily find out as a partition of. So one can find out a partition. Let us call it 0 a naught a1 equals to 1, such that, as we have done the same procedure in wherever we are talking about the path homotopy lifting or the path lifting, right? So this is so you can find out the partition of the closed interval 0, 1 such that the gamma of each subinterval will be contained in is either in U or in V. Okay. Great. Now we are looking at, so this is a general kind of partition that you can have using Lebesgue number theorem, which is related to the compactness of the closed interval 0, 1. But I am not dealing with this partition. We are going to refine it in such a way that each of the subdivisional point will be mapped to a point in the intersection domain. Okay, that means each of these A1, A2, and this AN minus 1 will be mapped to either will be mapped to the intersection U intersection V. Okay, so just by using using the connectedness of the subintervals, one can finally have a partition. Let us call it P star B naught less than B1 less than Bm equals to 1. Okay, such that gamma of Bk will be lying inside U intersection B, and gamma of each of the subintervals will be either in U or in V. Okay, and this is true for each. Let us call it K, I. Yeah, for each I. Okay, and then let me just let us draw a picture here through which you can visualize the situation perfectly. So what would be that? So this is your U and this is your V constituting the X. And we are specifying a point here, which is in U intersection V, and considering a loop based at X naught, right? Which is gamma. So that means so let us make, yeah, correct. So this is your gamma, right? So which is a loop based at X naught in X. Okay. Now what you can do? Now you can take, so if you look at the partition, so you will see that each of this, for each of the subdivisional point, this gamma of bi is in the intersection, right? That means, so this X naught is your, so this is your gamma 0, right? That means gamma b0, and also it is your gamma bn, right? And let us take gamma b1 here, and finally, and then just look at this path. Then you can take gamma b2 here, and then you are going to move here, right? So we are taking this to these 2 points for our discussion. Okay. But whatever be the subdivisional points, it will be mapped to in that section, intersection. Yeah. Now you can take the section of this gamma, you can mark them. That is, suppose you take, let us start from X naught and then going forward here along this direction, and then end at gamma b1. Okay. So let us call it gamma 1. Okay. And then again, you start from gamma b1 and move forward in this direction. Okay. And end at that point. And you can continue this process, and let us call it gamma 2. Okay. And you can continue this process for each of the image of corresponding subdivisional points. Okay. And you see that this gamma is nothing but, so that means, yeah. So this gamma, the path homotopy class of gamma. So if you want to impose the concatenation of paths, so this is nothing but gamma 1 star gamma 2, right? Star some gamma m. Am I correct? But this gamma 1, gamma 2, gamma m, these are actually paths. These are not loops. So I'm going to consider loops. I'm going to define loops here. So how to tackle this situation? Now, since we have assumed that U intersection B is path connected, so that means you can define paths connecting X naught to gamma B1. You can connect X naught to gamma B2, and so on. Okay, and let us call it alpha 1. Let us call it alpha 2. Okay, so using these paths, so what you can do, so now you are going to define loops through these paths. So let us take, so if you want to, so let us take sigma 1. Okay. So what is that? So here, alpha naught is the constant path x naught, and the end path alpha m will be the constant path x naught. Okay. So now I am trying to take that constant path, and starting from here, so we are moving around this path and coming to this gamma b1, right? And then move forward along this direction, tracing that path gamma 2, and then end at gamma b2. Okay. After that, from here, you are taking the inverse path gamma 2 bar to move back to the initial point. So that is your sigma 1. That means it is gamma naught star gamma. I'm sorry. What? Oh no, sorry. Sigma 1, right? Sigma 1 is this. This is sigma 2 actually. Yeah. This is sigma. This is alpha 1, and this is gamma 2 star gamma 2 bar. Yeah. Good. So your sigma 1 will be alpha naught star gamma 1 star alpha 1 bar. That means starting from here, moving along this path, and coming to this gamma b1, and then move around this path, and then coming back to h naught. Okay, so in this way, you can define generally. So we define sigma k as alpha k minus 1 star gamma k star alpha k bar, right? And if you look at the loops, you see that if you take that loop, you will see that this loop is lying in V, right? Not in U. I mean, solely not in U, right? Yeah. And if you consider the next one, that is sigma 2, it will be lying in U, right? So in this way, you can say that, so this is a loop in X based at X naught, which is lying either in U or in V. Great. So hence, the path homotopy class of gamma, it is nothing but it is the concatenation of these classes. Okay. And each of these class is either in the image of the fundamental group of U or in the image of the fundamental group of phi. So that's why you can say that pi 1x can be generated by the images of the fundamental groups of the respective domains U and V. Okay, and this proof gives you an indication to tackle the example of S for n greater or equal to 2, because on that case, so for that case, you are having one U and one V, which is a path connected space, right? So therefore, the fundamental group of Sn will be generated by the fundamental group of U and fundamental group of, the images of the fundamental group of U and images of the image of the fundamental group of V, which are nothing but trivial group. So that means they will generate ultimately a trivial group. Okay, so one can conclude that. So remark that the pi 1 Sn based at this, so this can be generated by the I star of pi 1 of U, J star of pi 1 of V, but these are trivial groups. So this implies this will be a trivial group for all n greater equal to 2. Okay. So that means Sn will be simply connected. Although S1 is not, but if you go up in the higher dimensions, then Sn will be simply connected. Okay. Great. So now I'm going to finish, I think, yeah. So, great. So I'm going to finish the course by stating the classical version of Seifert-Van Kampen theorem, which is like this. So let us attempt to state the Van Kampen theorem. Which says that, so if you consider a space X that will be satisfying the hypothesis of the previous discussion, that is, if it can be written as a union of two open sets whose intersection is a path connected space, and letting that X naught belongs to U intersection B, then you can consider the free product of groups this, and we are associating this group with the fundamental group of X, and suppose that J is a homomorphism between the free product of pi 1 U and pi 1 V to phi 1 X. Let J can be extended one minute. J will be the extended homomorphism induced by the inclusions. That means that we have already discussed, and this one. Now let us call it now J1, J2. Okay. And then so let this J will be the extended homomorphism, which is induced by these two inclusion J1 and J2. Then one can say that J is onto. Okay. This can be proved that this J is onto. So that means it is an epimorphism from this free product of two groups onto the fundamental group of X, and therefore by using first isomorphism theorem, you can say that we can determine the kernel of J. That kernel is nothing but it will be generated by the 1 minute. Yeah. So it will be generated by two elements. One is looking like this, I1 G inverse I2 G, and its conjugate K inverse. Okay. What is I1 and I2? So what is I1 and I2? So these are all the inclusions, the induced. So this I1 is the induced homomorphism from U intersection Bx naught to pi 1 U, and I2 is from U intersection V x naught to pi 1 phi. Okay. Yeah. And we are selecting this G from this one, this fundamental group, U intersection V x naught. Okay. Yeah. So in this way, so this means the fundamental group of X. Okay. So this can be, this is isomorphic to the free product of pi 1 U and pi 1 phi modulo kernel of J. And what is kernel of J? That has been given above, right? So which is the least normal subgroup. So this, yeah, right. So in particular, 1 minute. So in particular, if we let that U intersection V is simply connected, instead of taking only path connectedness, we are considering that this is a simply connected domain. Okay. Then Van Kampen theorem says that it will give you an isomorphism. Then Van Kampen, with the help of Van Kampen theorem, there exists an isomorphism. Let us call it K. Okay. From the free product of groups to the fundamental group of X. Okay. Yeah. And also remark if in addition to this, don't take, okay, we do not need to take that assumption. Let me just assume that V happens to be simply connected, then one can associate an isomorphism K from the fundamental group of U. Now see that here the fundamental group of V doesn't appear because it is simply connected. So it is a trivial group. Okay. So there exists an isomorphism from this modulo some normal subgroup N to the fundamental group of X, where this N will be, this is the least normal subgroup of the fundamental group of U containing the image. What is the image? Because we have already considered the induced homomorphism I1, right? From pi1 U intersection B to pi1 U. So we are considering, so this N will be the least normal subgroup of pi1 U containing the image I1 of pi1 U intersection V X naught. Okay? Correct. So if you look at some example, so you will see that suppose let us take okay, we can find out the okay, so let us consider the theta space. Okay, suppose it will be formed by taking three arcs. Let us make it a okay. So let it be here. Great. So let us take that arc as A. This is A. Sorry. This part as A. And this part as B. And take that one as C. Okay. So this is nothing but a graph having 4 vertices and 3 edges, right? So that means that in each case, so each pair of arc will intersect precisely at the endpoints. This one, right? Yeah. So it is a graph of 4 vertices and 6 edges, right? Oh, I'm sorry. Yeah. Sorry. So this theta, so this space, this is a, certainly it should be a, it is a T2 space, right? T2 space, and it can be shown that. So this is a, the fundamental group of this. It is non-abelian. Okay, because it is isomorphic to the fundamental group of the doubly punctured plane, and that will be isomorphic to the fundamental group of figure 8, and that fundamental group certainly will be non-abelian. Okay, so if you look at this diagram, so we can take that theta, it can be represented as the union of u and v, where we take that union, we take that u as it is the space punctured at some point, let us call it small p. This is small q. So this, and v will be theta minus q. Okay, so these are two open sets in theta, and if you look at the intersection, so this is theta minus p comma q, right? And suddenly, so if you look at the space, so you are deleting this one and this one. So then the remaining spaces are two open arcs, right? And that will be homeomorphic to some open interval, which is a contractible space, right? So therefore, so this is simply connected. Okay. Okay. And if you look at u, you will see that. So note that this u will have the same homotopy type of of yeah of B union C, right? Because you can shrunk this arc to this point, you can deform this arc to this point, right? And therefore, the U will be of same homotopy type as that of B union C, and this is actually homeomorphic to S1, right? At the same time, V will be having the same homotopy type of the other one, which is A union C, right? Which is homeomorphic with S1 again. And therefore, the fundamental groups of U and V can be taken as, let us take any point here. Suppose this is your X naught. So this is isomorphic to Z plus, and this is isomorphic with Z plus, right? And therefore, by the above observation, what can be said? So hence, the fundamental group of theta based at X naught. So this is nothing but, since if you look at this case, since it is simply connected, so you do not have any normal subgroup, any kernel. So kernel is going to be the singleton set. So therefore, this is isomorphic with the pre-product of these two groups. That is Z pre-product with Z. Okay. So this is a free group on two generators, right? Great. So, uh, so with this one, I need to stop. Okay. Any questions? You can also see that the if you are looking at double torus, so that will be, so the figure eight space will also be a deformation retract of the double torus. Okay. So in this way, you can compute the fundamental group of double torus also, right? So which is actually the fundamental group of figure eight. Okay. I mean, this is. I'm sorry. I'm sorry. Yeah. Actually, yeah. Deformation retract of figure eight space will be a deformation retract of. Actually, no. It will be a retract of double torus. I'm sorry, not deformation retract. Yeah. But at least you can say that the fundamental group of double torus will be non-abelian. Yeah. Great. So if there is no queries, no questions, so you can make comments. Yeah. So we can leave, right? So hope you have enjoyed my course, and I'm looking forward to see you again. Okay. Thank you so much, everyone. Yeah, for listening me so patiently.